Welcome to this model. In this model, we are going to see about the state transition diagram and the flow control and error control of TCP. To keep track of all the different events happening during connection establishment, connection termination, and data transfer, TCP can be specified as the finite state machine, as you can see in this diagram. So we can have a different time transition machine like synchronous plus time for wait and acknowledgement signal, and that it can be returned back by using listen and sync and asynchronous moment. And now let's see about the flow control in TCP. Any of the two parties involved in exchanging data can close the connection, although it is usually initiated by the client. Most implementations today allow two options for connection termination. One is three-way handshaking and the other is four-way handshaking with a half-close option. In three-way handshaking, most implementations today allow three-way handshaking only for connection termination. In normal situation, the client TCP, after receiving a close command from the client process, sends the first segment and the fin segment in which the fin flag is set. And the fin segment can include the last chunk of data sent by the client, or it can be just a control segment. And if it is only a control segment, it consumes only one sequence number. And that server TCP, after receiving the fin segment, informs its process of the situation and sends the second segment, that is fin plus acknowledgement segment, to confirm the receipt of the fin segment from the client and at the same time to announce the closing of connection in other direction. This segment can also contain the last chunk of the data from the server. If it doesn't carry data, it consumes only one sequence number. The client TCP sends the last segment and acknowledgement segment to confirm the receipt of the fin segment from the TCP server. And this segment contains the acknowledgement number, which is 1 plus the sequence number received in the fin segment from the server. And this segment cannot carry data and consumes no sequence number. And TCP uses a sliding window to handle flow control. As you can see in this diagram, the sliding window protocol used by TCP, however, is something between the go back end and the selective repeat sliding window. The sliding window protocol in TCP looks like the go back end protocol because it doesn't use NAC, that is negative acknowledgement, and it looks like selective repeat because the receiver holds the out of order segments until the missing ones arrive. There are two big differences between the sliding window and the one we used at the data link layer. First, the sliding window of TCP is byte oriented. The one which we discussed in the earlier model about the data link layer is frame oriented, but here it is byte oriented. Second, the TCP sliding window is of variable size, whereas for data link layer it is of fixed size. So here you can see the sliding window in TCP. The window spans a portion of the buffer containing bytes received from the process. The bytes inside the window are the bytes that can be in transit, and they can be sent without worrying about acknowledgement. The imaginary window has two walls, one left and one right. The window is opened and closed or shrunk, and these three activities, as we can see, are in the control of the receiver, not the sender, but the sender must obey the commands of the receiver in this matter. Opening a window means moving the right wall to the right, and this allows more new bytes in the buffer that are eligible for sending. Closing the window means moving the left wall to the right, and this means that some bytes have been acknowledged and the sender need not worry about them anymore. Shrinking the window means moving the right wall to the left. This is strongly discouraged and not allowed in some implementations because it means revoking the eligibility of some bytes for sending. And this is a problem if the sender has already sent these bytes. And you can notice that the left wall cannot move to the left because this would revoke some of the previously sent acknowledgements. So a sliding window is used to make transmission more efficient as well as to control the flow of data so that the destination doesn't become overwhelmed with the data. TCP sliding windows are byte oriented, as I said earlier. The size of the window at one end is determined by the lesser of the two values, receiver window and congestion window. The receiver window is the value advertised by the opposite end in a segment containing acknowledgement. It is the number of bytes the other end can accept before its buffer overflows and data are discarded. The congestion window is a value determined by the network to avoid congestion. And now let's move on to the next one, error control. TCP is a reliable transport layer protocol. This means that the application program that delivers a stream of data to TCP relies on TCP to deliver the entire stream to the application program on the other end in order without error or without any part lost or duplicated. TCP provides reliability using error control. Error control includes mechanisms for detecting corrupted segments, lost segments, out of order segments, and duplicated segments. So error control includes a mechanism for correcting errors after they are detected. Error detection and correction in TCP is achieved through the use of three simple tools called checksum, acknowledgement, and timeout. Let's see one by one. And this checksum, that is, each segment includes a checksum field which is used to check for a corrupted segment. If the segment is corrupted, it is discarded by the destination TCP and is considered as lost. TCP uses 16-bit checksum that is mandatory in every segment, and that 16-bit checksum is considered inadequate for the new transport layer, and that is a SCTP. However, it cannot be changed for TCP because this would involve reconfiguration of the entire header format. And next, TCP uses acknowledgements to confirm the receipt of data segments. Control segments that carry no data but consume a sequence number are also acknowledged. Acknowledgement segments are never acknowledged. So, acknowledged segments do not consume sequence number and are not acknowledged. The heart of the error control mechanism is the retransmission of segments. When a segment is corrupted, lost, or delayed, it is retransmitted. In modern implementations, a segment is retransmitted on two occasions: when a retransmission timer expires or when the sender receives three duplicate acknowledgements. We can notice that no retransmission occurs for segments that do not consume sequence number. In particular, there is no transmission for an acknowledgement segment. A recent implementation of TCP maintains one retransmission timer for all outstanding segments. When the timer matures, the earliest outstanding segment is retransmitted, even though lack of received acknowledgement can be due to a delayed segment, a delayed acknowledgement, or a lost acknowledgement. You can notice that no timeout timer is set for a segment that carries only an acknowledgement, which means that no such segment is reset. The value of RTO is dynamic in TCP and is updated based on the round trip time, that is RTT, of segments. And RTT is the time needed for a segment to reach a destination and for an acknowledgement to be received. It uses a backup strategy. And you can also retransmission after three duplicate acknowledgement segments. The previous rule about the retransmission of a segment is sufficient if the value of RTO is not very large. Sometimes one segment is lost and the receiver receives so many out of order segments that they cannot be saved. That is a limited buffer size, due to limited buffer size. So to alleviate this situation, most implementations today follow three duplicate acknowledgements rule to and retransmit the missing segment immediately. And this feature is referred to as fast retransmission. And when a segment is delayed or lost or discarded, the segments following that segment arrived out of order. Originally, TCP was designed to discard all out of order segments, resulting in the retransmission of missing segment and the following segments. But most implementations today do not discard the out of order segments. They store them temporarily and flag them as out of order segments until the missing segment arrives. So you can notice that out of order segments are not delivered to the process. TCP guarantees that the data are delivered to the process in order. So we can give some examples of scenarios that occur during the operation of TCP. In these scenarios, we can show a segment by rectangle, and if the segment carries data, we show the range of byte numbers and the value of this acknowledgement field. If it carries only an acknowledgement, we show only the acknowledgement number in the smaller box. Thank you.